Riemann sums and trapezoid rules. So I would expect something like the first sheet, which I don't think oh, here's one. Okay. So something like the first sheet, where I go left, right, mid, and then trapezoid. I like those 4 problems. But I haven't made, to my knowledge, I haven't made up a quiz yet, unless I have a handy dandy one stored. If I don't, let's just go ahead and say this. I'll just change the equation and give you something like this, okay?
Perfect.
And I'll give you more practice.
That's how we all.
But I'll change the equation, which means I'll need to change the picture, but it'll be very similar, okay? All right, so I wanted to go on and start this with this concept that this is another great thing I learned from a student of mine. There's a question that could possibly be on your next test, which I don't know when that is yet, but I'll sit down with the syllabus and the school calendar. I would like to have one more test this semester. I just had the stylus in my hand. Right, I just got the stylus in my hand. I put it in the box. Did you see me put it in the box? I have no idea why I put it in the box. Okay, so anyway, there's a question that I like to put on the test on this topic. Is like which one would give you an like underestimate or overestimate? Would it be right, left, mid, or trap? I've forgotten how they worded it. It was a multiple choice they gave years ago. It's very similar to this picture. And I think it was like, would a right-hand Riemann sum or a trapezoids give you an overestimate? I've forgotten the question. But I was going, the students had a question about it. It was maybe on an OAP exam before they saw it on the test, which could or maybe has already happened to you. We'll see. I can't remember. Well, I probably haven't given them to you yet on the 2003 exam. But I was explaining it like this. I'm like, well, if you did trapezoids, you know, as opposed to a Riemann sum or whatever, it would got, I mean, granted, I'm way up here on this big screen, but on your little sheet of paper, it's kind of hard to tell in the amount of room that you have. Like I was going on and on about, like I split it up into about 4, just naturally. It was a graph similar to like the one we've got. And I'm like, oh, well, you know, class, if we divide it up into trapezoids, it looks like that'll be an overestimate. But it was kind of hard to tell on our sheet of paper. And I had a student that had a great idea. They're like, can I tell you how I did it? I'm like, sure, that'd be great. They said, just do one. If they want to know if it's an overestimate or underestimate, just do one. Don't try to squeeze a bunch of them in there. So if I have a picture like this, and I want to know if a left-hand Riemann sum is going to be an underestimate, I'm just going to do one rectangle. And if I go from the left, it's an underestimate. If I go from the right, it's definitely going to be an overestimate. If I do one trapezoid, using both y values, it's definitely going to be over. I thought it was a great idea. If they like didn't tell me how many to do, and I just want to know if it's an overestimate or an underestimate, doing one's a great idea. Do y'all see what I mean? Okay. So we know under and overestimate for linearization is dependent on concavity. Which reminds me, like this. Merry Christmas. Happy
Thank you.
I don't remember grading them. Maybe I wasn't a generous man. I think most people kind of knew what you would maybe miss on this, but look over and you can ask questions.
Everyone knew like immediately
Yeah,
after.
I know.
I forgot. I'm just
So
afraid
once I
of
played
that.
over in my head.
Okay. So, anyway, that reminded me of that quiz. Did everybody get this back? Okay, so, if you're talking about an over or underestimate with estimating area, one is a good idea. If you're doing over or underestimate of a value using a linear approximation, then concavity is a good idea, second derivative. If you're talking about a tangent line, right now we're talking about area. Those have nothing to do with each other, right? Like we've just gotten through studying derivatives and all their properties, and we'll continue. That's never going to go away. But that's talking about rates of change, and all of a sudden I've switched gears and talking about area. Okay. All right. The words that we talked about in the last class, I think everybody was here to hear me talk about this. But if it's if I did it here from the left, those are left-hand Riemann sums. Right now, it's an underestimate in yellow, only because my graph is continually increasing in that way. Okay, it's an underestimate because my graph is increasing. What if my graph is increasing this way? And I go from the left. Still going to be an underestimate, right? But if I have a graph like this, then left's going to have some under and some over, okay? If they say that they wanted you to have a lower sum, which could also be the word inscribed, then you've got to make some decisions on what y values you're going to use. Here, if I want it to be inscribed, I'm going to have to go from the left, but on this one, do you see I would have to go from the right?
Yeah.
So those are inscribed. If they fall completely outside, that's called an upper sum or circumscribed, okay? Which we got through last time. All right, so now I wanted to do a couple of these problems just to start pointing out where in the world I'm going to go with this with hundreds of years of calculus. You should have been sort of thankful for your Thanksgiving homework because you're just adding up a few geometric figures, okay? Totally, hopefully thinking like I was thinking, like, okay, gotta be more to this. Given a choice right now, find the area of a regular shaped object, I would use mid or trap if I was gonna have to estimate it, okay? And don't forget the foundation of everything that is happening today. I think I'll go straight to mid. Oh, Grace?
So would you say mid is an under or overestimate, or is that just like a gloss one?
It all depends.
Like
On
let's
this
say on the
sheet, let me see what it is. I've not seen them ask that anyway. Mid's a good estimate. But that's a great question because you're leaving, it can really depend on the figure. It can't be as cut and dried as left and right. Right now, where are we going here? 0 to 4? It's a little bit under than the actual value of what's going on in here. But I just had to check it. I didn't know what was going to happen.
I think the last question on the homework, it went like this. So, what would your, because it still doesn't matter, like it won't be half under and half over, right?
Some of it could all be under, some of it could all be over, depending on where your mid happens.
But what if it's half under and half over?
That happens a lot, maybe.
So then is it,
They usually don't ask for under and over estimates for mid and trap. I'm sorry, for mid. They do for trap a lot. For mid, they usually don't ask that because you're getting some of both. Is that what y'all are both asking me, if it's an under and over estimate?
yeah.
Okay, they usually don't ask that for mid because they know that if you're just drawing a few rectangles, even if I do one mid, I guess I could. Let's go halfway and do one mid. Even with that, it's kind of hard to tell if that's under or over. Do you see what I mean? It's not as conclusive as left and right trap. It's a good question. Nobody's ever asked me that before, so I'm stumbling through my answer. But it's also a great thing to talk about. I guess you'll know that about me now. I never mind stumbling through an answer and going, I don't know, I'll look at it, and kind of stuff. I'll think about it. I think we all grow by doing that. But Caroline and Grace, I think from looking at that, we're like, I think it's under. I don't think I'm capturing everything that would be underneath the blue curve, but I haven't seen them ask that before. Okay.
Wouldn't
Anna?
it be like, if it's exponential, like only, wouldn't it always be an underestimate? And then if it's like the
The
opposite,
mid,
yeah, the mid. Because like there would always be more space
Since it's going up so steeply,
Yeah.
maybe?
Yeah.
Maybe.
And then if it's like concave down, wouldn't it always be an overestimate? Because
I haven't looked at it in the, I would have to think about it with you, I'll have to think about it some later also. I don't know that we could come to it always, just because there's so many ways an exponential could increase or
Yeah.
something could decrease. It's an interesting thing to think about. It looks like that would be true, Anna, but I don't even know if it matters with how many that I do. I see what you're saying, because it looks like there's gonna be a lot, I think you're saying there's gonna be a lot more,
Yeah.
not a lot, some more captured on the upper end than on the lower end. I don't know. So anyway, I know for sure that the mid on this problem is an underestimate. It kind of looked like it would be. All right, girls, let's do mid. And so anyway, if you go mid and you're doing 4, I want to also just lay the groundwork for where this is going. But anyway, if we do 4 from the middle, I would take 4 units and divide it into 4 equal parts, so the width of each rectangle was 1, which obviously you knew, okay? But if you don't know, if I wanted to do if I wanted to do 10 rectangles in here, I would have to say 4 divided by 10, right? If I wanted to do 8 rectangles in here, they'd each be half a unit wide. I know that y'all know that, but it's gonna be really big that you understand it in a more literal sense in just a minute, okay, conceptually. So anyway, 4 divided into 4 equal parts, each one is 1 unit wide. Watch out for charts or different things they might give you where every width is not the same. That can happen, okay? But these are all 4 divided by 4, they're all the same width. So I'm gonna factor out the width. If I go from the middle, so that means I'm gonna go from 1/2 and fill it in. I'm gonna go to 1 1/2 and fill it in. I'm gonna go to 2 1/2 and fill it in. And I'm gonna go 3 1/2 and fill it in. And what had been your luxurious homework then sort of got a little bit tougher with mid because you probably couldn't count and be completely sure what was happening, which also plays into what I want to do today. To actually find those heights of those that kind of land in between, I'd actually fill 1/2 into x squared. Is that what y'all did? All right, so you got 1/4. And then when I filled in 1 1/2 or 3/2, I got 9/4. And then when I filled in 2 1/2, what did that give me?
6.25.
Okay, I'm gonna keep, that's fine. If I fill in 2 1/2 or 5/2 and square it, that gives me 25/4.
And then 36.
And then 36/4, was that the next one?
49.
Oh, yeah,
I did mine all in decimals.
sorry, thank you. All right, so let's go to here. This is 3 1/2 or 7/2 squared is 49/4. And so I found all those y values and added them together. And I got 84/4 times 1, which was the width of each one. And so I got 21. Did y'all get 21 for the third
Yes.
answer? All right, for mid. So far, what was, okay, for mid you should have gotten 21. Here's my numbers: 1/4 Carla, 9/4, 25/4, and 49.
20 and a half. I got 20 and a half.
I guess it depends on
Did I do something wrong?
It just depends on the values that you
What you
choose.
estimate the first.
Okay, wait. We should all get the same answer now. I don't know about what you thought at homework, but if they say from the middle, I have to fill 1/2 into the function x squared. Like if you were estimating these y values right here, if you're actually given a function y equals x squared, you should fill in between 0 and 1. You should fill in 1/2 and square it. And between 1 and 2, you should fill in 1 1/2 or 3/2 and square it. And between 2 and 3, if you want that y value to that blue curve, then you know it's 5/2 squared, which is 25/4. And then between 3 and 4 is 3 1/2 or 7/2 filled in. I know is 49/4. So let's pause for the people that didn't get 21 because I need to fix that for quizzes and tests and stuff.
I'll
So,
figure it out.
Elena, like, do you see where I got my numbers?
Yeah.
Okay. Carlo, did you get the right numbers and maybe just added wrong?
I'm gonna redo it.
Okay. Do you understand what I'm saying?
Yeah, no,
Okay. Anna, do you understand what I'm saying? Okay. I fully understand and kind of like the idea if you just looked at the graph and estimated, But what I've got to make sure that you do is, recently I gave you a problem on a test or a quiz that had a graph and a table of values. And you didn't have an equation, but you were supposed to get all your numbers out of the table because they gave them to you. Do y'all kind of remember that problem? It looked like this.
It was on that homework.
It was some sort of velocity problem, and it was that R prime of, yeah, okay, it was homework. Anyway, some people were trying to estimate the values from the graph when you had a table of values sitting right there. Or if they give you the equation, they expect you to find the actual real value. If you have to approximate, then you have to approximate, but they're not going to do that to you in this sense. So did everybody else get 21? Okay. What was the answer to the left? I didn't write mine down. 14, and it was pretty low. And the one from the right must have been about
30.
Oh, really high. And now we've got 21, so we're thinking that's probably around 21-ish. Then trapezoid. If I do trapezoids, okay, girls, back to trapezoids. Okay, if I do trapezoids, then you need both values on either end. All right, so I'm going to make this trapezoid, I'm going to make this trapezoid, I'm going to make this trapezoid, and that trapezoid was actually a triangle, wasn't it?
Yes.
Okay, so I'm going to say 1/2 base 1 plus base 2 times height, 1/2 base 1 plus base 2 times height, and I'm going to show you the trapezoid rule today that I told you last class not to memorize, but I'm going to show it to you just so you're versed in it if you hear somebody talking about the trapezoid rule. Do not use it on the AP exam, and I'll talk about why that is, okay? One reason is, why in the world would you learn a formula when all you've got to do is add up 2 or 3 trapezoids, okay? Instead of the big, ugly formula I'm going to show you. Another reason is many times they'll just give you a chart, and if somebody uses the trapezoid rule, they're going to miss it many times because a lot of times the trapezoid rule only works if the stuff in the chart they give you is all spaced out evenly, okay? And sometimes everything we've done so far is spaced out evenly, but I'll show you in a minute why maybe that wouldn't be true. All right? Okay, so anyway, let's finish this and then we'll go on. My first y value was 0, and then the next base was 1 squared, and then didn't that repeat in the next trapezoid? All right, so that would be 1 plus 2 squared was 4, and then that repeated, and that's going to be real important to our formula. 4 plus 3 squared was 9, and then that repeated until I got to 4 squared, which is 16. The height of each one of these trapezoids turned on its side is 1. Okay? And I think that added up to 22.
Yes.
22. So we can see the trapezoids too much, but I'm thinking it's got to be somewhere around 21, 22 is really the area in this curve. Okay? Now, why would let's talk about Riemann, this famous mathematician, I think in the 1800s, 17 or 1800s. Really after Newton and Leibniz, which we'll also talk about. And we're going to talk about 4 famous mathematicians today, and I'll pull up some information on some of them maybe because I love history. Riemann's son many times is not literally, he kind of played around with this. He's like, what if I do a few like little rectangles here to try to capture this, and then maybe I could do one big rectangle, to that's not a good, sorry, it would not be that. I didn't want to do that. Let's see.
Oh no.
All right. Anyway, let me see if I can draw one. Sometimes people did different size rectangles to try to capture a lot of area, and that wouldn't be a good idea. Do you see I left out a bunch of area there? So I'm doing this really poorly, but go ahead.
Could you make a triangle out of that?
Yeah, but then that wouldn't be a Riemann sum. So let me draw you another. A Riemann sum is exclusively you're talking about rectangles. Yes, there was that method of exhaustion that people like Archimedes used, where they were like, I'm going to grab as much of this as I can, and then I'm going to make this a triangle, which is going to be an overestimate. After a while, they kind of left that method of exhaustion where you do left with triangles added onto them because you had so many different figures, and I'll show you why they went exclusively to these rectangles. Because right now, what Caroline noticed is that method of exhaustion, which is really how Archimedes found the area of a circle, is he divided up into a bunch of polygons and added them all together. Okay? But we're going to find we can divide it up into rectangles. What I'm saying here is maybe I could capture a lot of the area with a rectangle this wide, and then I might want skinnier ones as I get toward the end. After a while, they didn't always use the same width rectangle if you felt like you could capture a lot of area with one. So you got to watch for that in here, especially when they give you a chart. Many times they'll say, divide it up into 3 rectangles of equal width, okay? Or if they say what you've seen so far. It's usually when you have a chart that you really have to watch the width. They may skip by 3, and then 2, and then 1, and then 5. You've got to look at the width of each one. That's why I have you, I hate this word, trained, to go length times width plus length times width times length. Don't try to be tricky. Enjoy adding up 3 or 4 rectangles, okay? Don't try to be tricky, but watch out. All right, now, let's go on and talk about the trapezoid rule, okay? You don't have to write this down. There's also something called Simpson's formula or Simpson's rule, where I kind of made a reference to it the other day. Simpson came in, and there's actually an unbelievably cool formula where he tried to put little quadratics in here and add up what was underneath those. Like, do you see how he divided them up into, the quadratics don't quite fit, but it's better than trap. Okay, but there's a reason you may wonder, well, what if there's mid and trapezoid and Simpson's formula that work really well, then why is there anything else you're going to teach us, okay? So we'll see. Trapezoid rule goes like this. If you're going to say 1/2 base 1 plus base 2 times height plus 1/2 base 2 plus base 3 times height, are y'all with me here?
Yes.
All right, plus 1/2, what's going to happen here? Base 3 is going to repeat in base 4. And so we'll just do these. No, because I've called this base 1. So I need to go 1/2 base 4 plus base 5. I'm going to change my subscripts though. We need to get used to this anyway. I'm going to call this first one b sub 0, my initial one. I think y'all have done that in science some, where that's your initial value. And this would really be b sub 1, b sub 2, b sub 3, and b sub 4. Does that make sense? So my starting place is just b sub 0. So this would be my first base, my second base, and trapezoid rule, I'm not seeing it named for anybody's name attached to it like Simpson's formula, because, you know, they'd be lucky to have their name attached to it, kind of like Rolle's theorem, corollary to the mean value theorem, like you could find the slope between these 2 points, or you could find the slope between these 2 points, and you go, aha, that slope would be 0, so you'd be finding a critical number. But you're just still doing the mean value theorem, the difference between 2 points. The trapezoid rule, I don't know who the first one that noticed it, but you know what, y'all would be the ones who noticed it too. You'd go, I don't want to keep doing that. And this is the only thing I did when I was in college, Cal 1. I just did the trapezoid rule whenever I memorized this formula I'm about to show you, which is embarrassing. But anyway, it's in our book. Most everybody memorizes it on the college level, which is where we are. So anyway, here it is. Do y'all see that they have the same 1/2 and the same height? So I factored that out. I think the only reason they write it this way, I told you the other day, is to call to mind just like 1/2 base times height, but trapezoid has 2 bases. Okay. And now if I factor out 1/2 in height, I have b sub 0. How many b sub 1s will I have? 2. How many b sub 2s will I have? How many b sub 3s will I have? And the ones on the end just count once, right? So isn't this going to be shared by this trapezoid and by that trapezoid? So these just count one time, and all of the insides are shared on the trapezoid. All right? Now, what are these b's? Let's be more clear. Aren't these y values or f of x's? So I have 1/2 h, and I have y sub 0, 2y sub 1, 2y sub 2, 2y sub 3, and y sub 4. All right, now how do I get this height? How do I get how tall these are when they're turned on their side? When you say, go ahead.
Because the height would be the width.
The height would be the width, and so you would say, if I'm going from A to B, it would be B minus A divided into 4 equal parts. I haven't said how far I'm going, but y'all see if I'm going from 0 to 8 or whatever. Is everybody okay with that?
Yes.
Okay. So this is B minus A divided into n equal parts, whatever number that I tell you. And if you look it up in a book or on Khan Academy or whatever, this is the trapezoid rule. And whenever somebody uses that on the AP exam when we're reading them in the summer, we just sort of shake our heads and go, sorry, gone. Because if they just start grabbing numbers out of the chart, they're going to miss it because this might not be the same thing every time. Do y'all see what I mean?
Yes.
Okay, so please just use the trapezoid rule like I've already taught it to you. Just go 1/2 base 1 plus base 2 times whatever width they give you in the chart. And I'll keep talking about that as time goes on. So the real trapezoid rule is this: 1/2 b minus, so it's not that, it's this. This is what I memorized. And honestly didn't really process at all what I was doing. So it's b minus a over 2n times y sub 0 plus 2y sub 1 plus 2y sub 2 plus ... y sub n. And that's written in books. That's what I memorized. And I looked over it before the test to make sure I had it in my head, which is embarrassing. Okay? If they said go from 0 to 5 and do 10 rectangles, I would go b minus a over 2 times 10. And then I would find my y values. I could have just added up however many trapezoids they gave me. Did y'all see the difference? Did y'all see where b minus a over 2n came from? So it's still 1/2 the width times the heights. Y'all okay with that? So you don't have to know that. In fact, please don't. Don't use that. But at least you've seen it. If somebody starts talking about trapezoid rules, you know. Simpson's rule with the quadratics, I don't even remember it, but it's kind of cool. It goes 1, 3, 1, 3, 1, or something weird. But it's similar to this. It has a different thing on the outside. I had to apply it sometimes, but we're not going to be asking you Simpson's rule. And you'll see why a lot of this just became obsolete. What they were struggling with. Some people in the late 1600s with Newton and Leibniz, some of what we're doing became obsolete, but we find that Gauss and Riemann came after them historically, and they still wanted to plow back through to make some sense of what I'm going to show you today. And you can't forget what I'm telling you once I show you the like coolest thing ever. All right, so now I want to go to this. Let's go to your second page. What you want to really watch for is if we're doing a right-hand Riemann sum, by the way, if I'm doing from the right, don't I need these y values?
Yeah.
If I'm doing from the left, I need these y values. And my widths are going to be right here. All right, does everybody understand how I pick left and right? Okay. So if I did it from the right, now be careful. How big is this first width? 2. And how big is the next width? 2. So you could have found all the heights and multiplied it by 2. But watch out, because from what I give you from AP exams, sometimes those are different. So don't get lazy. Watch and see, they may have just gone 1 unit there, and they might go 6 units next. Please be careful. All right, now if I'm doing it from the right, I needed 8, 14, 18, and 21. And what did that give us? What y'all get for 2? 122? Okay. All right. Is everybody okay with that? All right, if I do from the middle, for number 3, if I'm going to do 2 equally spaced subintervals. So I'm going 8 units. I'm dividing it up into 2 equally spaced, so each one was 4 units wide. All right, if I'm going from 0 to 8, using a mid, what value do I need to fill in? if I'm doing mid, well, first of all, if I'm going from 0 to 8 with 4 rectangles, sorry, I'll have 2 rectangles that are how wide? 0 to 8, I have 2 rectangles that are 4 units wide, right? So these are 4 units wide, and these are 4 units wide. Now, if I was going to do left, I would use this value and this value for my 2 rectangles. If I was going to do right, I would use this one. No, not that one. If I was doing it from the right, I would use only this one and this one. But what did they say to do from the middle? So I'm going to go from 0 to 4, but I'm going to fill in 2 and get 8 as my height. Then I'm going to go from 4 to 8, but I'm going to fill in 6. Did y'all do that?
Yeah.
All right, what did that give you? I don't know. I didn't write it down.
104. Yeah.
Okay. So everybody get 122 and 104. All right, so the third page. Let me call out the answers that I got there. I got 8 both times. Did y'all get 8 both times?
Yeah.
Okay, so on the B part, we're doing trapezoids, 4 trapezoids. So first we did 2 trapezoids on the A part, and then we did 4 trapezoids on the B part. All right, Grace, which one did you not get 8 on?
For me, I got 7.
Okay.
Probably calculations.
All right, so I'm going to do it. 1/2 base times height. 1/2 base 1 plus base 2 times height. 1/2 base 1 plus base 2 times height. 1/2 base 1 plus base 2 times height. Now we're doing 4 units, 4 trapezoids, so we're assuming they're equal areas. So these were all 1 unit wide. And then to find my first base, I filled 0 into my function. And did I get 0? Okay. For the next one, I filled in f of 1 into my function, and I got 7/4, which I knew would repeat. It'd be part of both trapezoids. And then I found f of 2, and f of 2 was 2. And then I found f of 3, which I got 9/4. And so that's part of both of these trapezoids. And then finally I found f of 4, and I got 4. And when I added all of those up, I got 8. So I don't know if that helps or not.
Yeah, I got all the same numbers, so it's probably just.
Okay. Interesting, you got 8 with 2 and 8 with 4. Probably because of the shape of the grass. Okay? All right, so your quiz, I'll just go ahead and say it's going to be, oh, here it is. Like this first page, but I'll just change the equation.
So it's like this worksheet, just for the
Yeah, and if you can do the first, but I mean, it continues on, but you'll actually have a picture.
Okay.
All right, so now let's go to this. All right, all right, here's x squared, like on the first page. And you did this, 4 rectangles from the middle, and they got 21 right here. Okay, they tell us the actual area is 21 1/3. Okay, I'm going to show you. All right, so, but 4 rectangles is a really bad idea. So why don't we do 14 rectangles? All right, watch the numbers, 21.3 already, and I've captured a lot more area. So what would you say about these rectangles? The what? The smaller they are, which means the more the better?
Yeah.
Okay, so how about 140 of them?
And then why did it change for the last question we just did with 2 and 4? Oh, that was trapezoids. Never
That
mind.
was trapezoids. We can actually look at the actual area under that. So look how close it is. It's off by like 1/10,000th of a place. Girls, please watch. Makes me nervous with the computer flipping. You really, really want to see this. What about 1,400?
That's gonna be so close. That's gonna be
Was that many? It's just gonna be.
This algorithm.
Oh my
God.
god.
Alright, but which of us in here wants to add up 1,400 rectangles? So we're like, no, I don't want to do that, okay? I don't even want to add up 14 because, like, you know, Grace and myself and some other people made computational errors, even for the calculator. I'm like, I don't want to do 14. I just want to do 2, 3, maybe 4. Okay? So I'm going to teach you how to add up 1,400 rectangles. Girls, 1,400 looks pretty good, but the estimated area and the actual area, if I went out a few more decimal places, would still be off. This is just on a screen in our classroom. If this was ginormous, like the area, the volume of the Earth, or the area enclosed, you know, inside the space shuttle, or the volume also, but something really big, you still think there'd probably be some gaps in your little white spaces, okay? All right, so that's mid. Let's look at right. We like mid. Let's look at right. Is there any difference? I think it's already done. I'm not sure. Okay, but did y'all see how all of a sudden it just colored it in? Let's go back to what Caroline said. I'm sorry, Emma. I just did that for the first time in 2 years. Sorry about that.
No, it's fine. So much better this time. Oh my god.
I'm so sorry. Okay, so Emma said the thinner the better. I think is what she said. Why is this coloring it in? The lines, if I go back to 4, if I go back to 4, the lines are black. If I go to 14, so what has happened in light of what Emma said? What's happened? They've gotten so incredibly thin, the lines have come together, so it's basically like Emma and I are adding up strands of hair or toothpicks or something. Okay? So do you see this like strand of hair? Those things have a tiny, tiny, tiny width. Okay? All right, so let's do this for the next few minutes. Let's all close our computers or push them down so that you may not want to lose whatever it is that you're doing besides my class, but you really want to see this, okay? What I'm about to do, you can just watch. I think it's better that you watch. I will not, I shouldn't say this before I start, but I can trust y'all. You're not going to have to do this per se, okay? I'll show you the parts you're going to have to do, but you want to see hundreds of years in calculus unravel in a few minutes, okay?
Wow.
And you should all say a career that I'll make a careless mistake also. By the way, the bulletin from church, did I show you this last time?
No.
My husband looked over at me. He's a math major too, but I'm totally listening to the sermon. But I also thought that I would teach this like the last Monday. So in church, I was like he's like, what are you doing? I'm like, fundamental handbook calculus. He goes, okay. So then he just kept on listening. But anyway, it makes sense. Yeah, it makes perfect sense. Okay. So I have a picture of a napkin from our first date. I'll have to show y'all sometime. No, not our first date. One of our first dates, I'm like, he's a math major, so I'm like, okay, I got this question for you, see if you can get it right. And he's like, are you serious? Is this like pressure? And I'm like, how quickly do you have to react if somebody's doing a 90-mile-an-hour fastball over, you got to figure out when it's going to pass home plate. You got it right. I'll show you. All right, so anyway.
Did you ever get dating him and he got it wrong?
And that's
Yeah.
how you
Yeah. Okay, so we're going to take y equals 3x plus 1, and we're going to be mathematicians of old. We're going to go from 0 to 3. We're going to divide it into n number of rectangles. Now, on this church bulletin, I'm going to actually write a number. I'm going to turn it on where you can't see it. All right, it's in purple. I'll have Elena verify it in a little while, okay? But the reason I do this is because I want you to know there's an actual number here. So every time I write n, it's a number, it's a constant. So I want to really drive that point home. We're gonna have some variables in this. N is a constant, it's on the sheet of paper. I just won't tell you what it is, okay? All right, so, if I would tell you what it is, would you agree that you would go 3 minus 0 units and divide it into n equal parts? Okay, so let's go back to this. All right, so right here, what if I took 4 units and divided it into 8 equal parts? Then that's 4 minus 0, and so they're each going to be half a unit wide. Would that work if I'm going to go from like 2 to 5 and I want 6 rectangles? Could you say 5 minus 2 is 3 spaces divided by 6, they'd each be half a unit wide? Then what would you do is you move half a unit, okay? Then well, first of all, you know this is a consistent half, right? So you know your width is a half. I'm doing equal widths right now because there's no reason to do otherwise, okay? They're equal widths. I'll get to that in a minute. Now, how will I find out how high each one of these is? Don't I have to fill it into the function?
Yeah.
I have to find f of 0, f of 1/2, f of, this is 0 1/2, this is 1 1/2. Then I'm going to fill in my second 1/2. So for argument's sake, I'm going to call it 2 halves. Wouldn't that be true?
Yeah.
Then I'm going to fill in my 1, 2, my third 1/2, all the way until I get to my 8th 1/2. And I'm doing it from the right now, by the way. So I don't even really need this one, so I'm sorry, I was wrong there. If I'm doing it from the right, I need my first 1/2, my second 1/2, my third 1/2, my fourth 1/2, and I don't just need it, don't I need to fill it in to get the height? Okay, so this is my first 1/2, my second 1/2, this is my third 1/2. Would this one be my fourth 1/2? That would give me 2, wouldn't it? All the way to my 6th 1/2 or my 8th 1/2 filled into the function. Okay, so going back to our slide. Okay, so I'm going 3 units and dividing it in equal parts, and so I'm going to add up. Y'all okay if I use sigma? So just for a way for me to say I'm going to add up a bunch of rectangles. Lengths times widths. Y'all okay with that? Length times width. The width of each one is going to be 3 divided by whatever number I put on this sheet of paper. Okay? 3 divided by whatever number I put on that sheet of paper. Now, what is my height going to be? Length times width. This is y equals 3x plus 1. Okay? And so I'm going from 0 to 3. So then I need to stop and fill some of these in as I go. I need to fill in my first 3 over n. Then do I need to fill in my second 3 over n, all the way to my last 3 over n, which I'd be filling in 3. Do y'all see how that works?
Yes.
Okay, 3 over n is how wide each one is, and so then you move by that. So to write out, I don't know, y'all don't know what n is, so I don't know how many of these I need to write out, so that's why I'm using sigma notation. All right, so if I do width, 3 over n times length is a y value. So I'm going to have to say f of 3k over n as k goes from 1 to n. Let's pause. If I fill in 1, n is not 6 right now. That is not what's on the sheet of paper, okay? But if n was 6, would 3 over 6 give me the width of each rectangle?
Yes.
If n is 6, wouldn't each of them be half a unit wide?
Yes.
And then what would this mean? If k is 1, then I'll fill in 1 times 3 over 6. I'll fill in 1/2 and find this y value. Then what happens when k is 2 is it cycles through the integers. When k is 2, I'm going to fill in 3 over 6. I'm going to fill in my second one. Do y'all see how that's working? My second 1/2 is actually 1. Are y'all okay with all of that? All the way until my last one. These are from the right. Okay, now let me go to another slide. I'll come back to that. So there's my notation. Do y'all see I'm adding up rectangles, length times width after giving you days to do that? in a simple fashion. Bless you. All right, let's get some sigma rules down. If I have a sum of 3k as k goes from 1 to 6, that's going to be 18. How did I get it that fast?
6 times.
All right, so I have 3 times, oh, I don't think it's 18, never mind. Sorry, that would be if I had this. Might as well go in and address that since I made that mistake. This would be 18. This does not have a variable in it, so this is just like the line y equals 3, okay? So what's your first value? 3. What's your second value? 3. Your third value? So do y'all see the fast way to do it is just you have 3 6 times?
Yes.
All right, because each value is 3. All right, so over here I better slow down. I have 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, 3 times 6. So that's what our sigma notation means, okay? That gives me 9, well, suffice it to say, couldn't I have done this?
3 times 9 plus 2 Yes.
I want to be really careful with what I'm allowed to do mathematically, okay? If I have sine 2x, I can't just go, oh, I don't want to do that. I'll just go 2 sine x instead. Are you able to take this 2 out? You can't factor that out, okay? If I have the logarithm of 2k, I'm not able to just go, oh, well, I don't want that. I want 2 times the logarithm of k. That's not all right. But with sigmas, I'm allowed to factor that coefficient out. Do y'all see it wouldn't make any difference as I write it out?
No.
That's going to be big, okay? So now let's go back to this slide. Sorry, I had a few of them written down I wanted to do. This is not even the right sheet. Okay. So moving forward, after we got our sigma rules down, because we're going to need them. All right, n is a constant. So according to what we just learned, could not factor that out. Each one's going to be, you've gotten aggravated in your homework, probably even with 4, having to go, this comes 1/2, this comes 1/2, this comes 1/2, to where you want to factor it out. All right, so I'm going to factor out the 3 over n outside my sigma. Now I'm going to start filling these in as k goes from 1 to n. All right, my function, girls, watch carefully. My function is 3x plus 1. Don't I need to fill my first 3 over n to get my y value? My second 3 over n to get my y value. So I'm actually going to fill 3k over n into my function for x. So I'm putting this in for x. And so if I was actually doing this with a number in front of you right now, I would say 3k over n plus 1. All right, let's look at what this is doing, okay? If k is 1, y'all see it's going to fill my first subdivision in to my function and find a y value. Sorry, if I had to do it over again, I probably wouldn't have 2 3's in this. Should maybe make this 2x plus 1 from 0 to 3. Those are 2 different 3's. Y'all see I'm going to fill in my first one times 3 and add 1 and get a y. Fill in my second one times 3, add 1 and get a y. Okay? So this is making me cycle through all of that. All right, so now I have 3 over n times the sum as k goes from 1 to n of 9k. Really fun. All right, 9.
Oh, I like her shoes. I want to start wearing them.
Not sure what happened. Okay, so this is going to be 9k over n plus the sum as k goes from 1 to n over 1. Alright, girls, something I didn't say before. If I want the sum of 2k plus 4, and k goes from 1 to 3, let's do it. So I'm off to the side, off-road, not people working on this problem right now. I'm just going to establish something else with sickness. Okay? 2 times 1 plus 4. Alright, this is going to be 2 times 2 plus 4, and 2 times 3 plus 4. Would it have been okay for me to distribute this 6?
Yes.
Alright, because didn't I get 3 of those 4s? So it's okay for me to add this up and then add this up and then add them together. That's a big deal. There's so many functions that you cannot distribute. What are you doing? You stop your hands on your computer. What are you doing?
I'm typing a list.
Is it due soon? Do you have to
No,
do that?
it's just a list of things I need to do.
It's okay, as long as you're listening. You're just typing up your list of things to do, okay? But keep listening. All right, now, so I can add all of this up or I can add them up individually. Any questions so far? Because you need to understand this to a degree, okay? All right, so girls, you got to stay with me, all right? This is 3 over n. On this first sum, I can factor out the constant, 9 over n. Remember, n's on that sheet of paper. Times the sum of k as k goes from 1 to n. Somebody in the room knows what that sum is. What is it? N. It's 1 plus 1 plus 1 plus 1 n times, right? So isn't it just 1 n times? You would add up 1 that many times. So whatever n is, I've added it up that much. So this is n. Okay. Now, this is adding up a bunch of integers. Wouldn't that add up 1, 2, 3, 4, 5, 6, 7? Okay? So you've heard this story before, I'm sure. Gauss. He's recognized as being one of the great mathematicians of all time, but right here. The most well-known story is a tale from when Gauss was still in primary school. One day Gauss's teacher asked the class to add the numbers 1 to 100, assuming the task would occupy them for quite a while. If today I had come in and said, add up the numbers from 1 to 100, even with your calculator, which they didn't have back then, it's very time consuming because you have to keep a running total. Do y'all see what I mean?
Or you could just do the
Okay? Right. You don't have to do it right now, but y'all see if I asked you to add up the numbers 1 to 25, it would be a bit aggravating because you'd have to keep a running total if I didn't let you have your calculator. Even if you did, I'd rather know this because I don't want to get out my calculator, type in the sigma, get all the right format in, and find the sum, and I could do it with what little Gauss found, okay? So what little Gauss found, he immediately walked up with 50-50, okay? That's because he found that he could take the number times, I'll write it down for you. So Gauss already had this little formula figured out when he was in primary school. So if I want the sum of a certain number of integers, as k goes from 1 to n, I can say n times n plus 1 over 2. It works every time. Let's do this. Okay, so if I want the sum of k as k goes from 1 to 5, I could go 1 plus 2 plus 3 plus 4 plus 5, which gives me 15. Okay, but could I have gone the number of terms, 5, times 6 divided by 2? Now that's, so it's n times n plus 1 over 2 will always get you the right number. Caroline?
Okay.
I'm sorry, you were just looking confused. So.
Yeah. The equation makes sense.
Okay. You know, you'd have to read where he came up with it, but it always works. Now, I would just add up 5, but if I have to add up 500 or just a second ago 1400, aren't I thankful for Gauss's work?
Yeah, I didn't think just like.
Okay.
So
All right, so
Match like figure.
like that young.
So we're going to use Gauss's formulas.
Like the teacher just said she was like lazy for a while. And then
Yeah, she probably was going to like
Yeah,
write letters or grade
Yeah,
papers or
Sean was
something.
dead
Did
for
he
like
ruin
a
it?
day.
And you were, yeah, then he's up at her desk
Why
with
did you
50
feel burnt out?
She probably just gave him something else to do while
Wait,
the rest of them
what
figured
year
it
was
out.
this in?
Gauss was in the,
Mr. Hill figured it out.
2011.
so actually, anyway, he lived in the late 1700s, early 1800s. So Newton and Leibniz, who really, they did something else here. I don't know what it is. They did, I'm combining, like I said, hundreds of years of mathematics to show you what Leibniz and Newton found in the 1600s. Okay? All right, so back to this. All right, now this is where I've got to be really careful that I don't mess up. So you may be a little aggravated. I'm not going to cancel anything out, but in my experience, I usually mess things up. So I'm just going to be really careful if I try to get too tricky. So this is 9 over n times the sum of however many integers is written on that paper would be that number times that number plus 1 divided by 2. Okay? Plus this n that Sophia already knew about. So now I have 27. I'm going to be really careful. That's n squared plus n. Over, the bottom's going to be 2n squared. I just distributed that, hopefully correctly. That's going to be 3. All right, but I'm going to write it as 3n over n because I want a common denominator. A common denominator is 2n squared. So what am I going to have to multiply this by? 2n, which is going to give me 27n squared plus n plus 6n squared. So that gives me 33n squared plus n over 2n squared. Okay? And so now I will let her find the purple number on this page.
Do I say it?
Yes,
4.
4.
Yay!
In which case, if you have like tomatoes or water balloons or something, you should throw them at me, because wouldn't you have much rather just added up 4 stupid rectangles?
Yes.
Okay? Alright, wouldn't it be awesome if I'll do that? Anyway, so let's do it. 30, I need a calculator now. 16 plus 4 over 2 times 16. Alright, somebody give me that number real quickly. 33 times 16 plus 4 divided by 32. Do you have it, Grace?
16.625.
Is that what everybody got? 16.625? All right, let's go to this. Girls, listen up. Shh. All right, my formula is 3x plus 1, 0 to 3, with 4 rectangles. Y'all said 16, didn't you?
16.625.
It's getting 19.875.
No, that's
The average area.
I'm doing the estimated area with 4 rectangles. Was it 3x plus 1?
You found the actual area?
No, I was just trying to do it with 4 rectangles. Those should be the same number. All right, it should have come up 33n squared.
Wait, but how was that?
On the left.
I went 0 to 3, didn't I? With the right?
Yeah, you did.
Let me see your calculator. Y'all both got the same answer, but let me be sure. Yeah, you did it right. What'd you do?
I didn't really study too because I got in the end I got 33 and 27 over 2 n. That's what I got in the end. I got 92.
From here?
How was the answer?
Right, that's what I mean. So what, if I mess up my audio?
Equations end up different.
Okay, what's your equation?
33n plus 27 over 2n.
Oh, I didn't distribute a 27. That's what it was. Thanks, Sophia. All right, this is, girls, listen, sorry. Thank you so much, Sophia. This is where I tend to mess up. This was 27n squared. This should have been plus 27n. Do y'all see I didn't distribute the 27 to this n? Okay, so this should be 27. Thank you for saving me because I really needed 4 to work. All right, so this is 33n squared plus 27n. Which you're right, Sophia, I could cancel out an n, but I'm not going to. All right, so this is 27 times 4. All right, sorry, I almost always mess this up. Sir Grace. All right, now everybody be quiet. Computer's closed. All right, listen up. So the big drum roll there would have been I filled in 4 and got the exact answer that they got on the little Riemann sum calculator. Do y'all see what I mean?
Yeah.
Wow, it's really cool, Mrs. Airy, but I would have rather just added up 4 rectangles and gotten 19.1. We know it's a much bigger, it's way an overestimate with just 4 from the right, okay? Obviously, I'm being a bit facetious, okay? What I could have written in there was 4,000. I don't want to add up 4,000 rectangles, but if I do all of this, what do I just have to fill in right here? 4,000.
That is true.
So if I do all this, it doesn't matter how many. Do y'all get what I'm saying? Now, if somebody tells me to do, girls, listen. If somebody tells me to do 4, I'm just going to do 4 rectangles. If somebody tells me to do 4,000, I'm going to do this. I'm going to do sigma. Okay? However, the what? Do y'all want 4,000 rectangles? How many do y'all want?
An infinite 14 million.
I'm going to take the limit of this as the number of rectangles approaches infinity.
We were like,
If I have an infinite number of rectangles,
14.
girls, as Emma said earlier, if I have that many rectangles, the more the better. They're going to be infinitely small. They're going to be like adding up strands of hair. They're going to be right next to each other. It will color it in. Are y'all okay with that?
Yes.
All right. So, go back to your limit rules. If you're going, hey, I really, really need you not to talk right now. So if you're tempted to, please don't. Just listen. I get through this. I'm going to start all this over in the next class, and it's kind of got a bit. Do y'all remember our limit rules where you look at the highest powers? We get 16.5.
Yes.
All right, let's see how we did. I was kind of moving through that really fast because I thought someone might stop me with this picture. I shouldn't even be doing calculus to this, okay? Of course, I wanted to, and I didn't want you to stop me. But 3x plus 1 is linear. This just makes a big trapezoid, doesn't it?
Awkward, but none of us.
Doesn't that just make a big trapezoid? If I want the area under the curve, I'm not doing calculus, okay? I'm going to go 1/2. Base 1 is 1. The last base, 3 times 3 plus 1 is 10. And the width of this big trapezoid is 3. That'll give me 33 over 2, or
16.5.
Wow.
That's crazy.
point being,
My mind is like,
I could always do what I just did to find the area under the curve of things I don't know anything about, okay? I'll probably take you through another one of those later, but let me finish the last few minutes with what happened with Lynn is new. Because that's what people were doing to find the area under irregular shaped objects. They were going like this. They were going, I know 4's not enough. I know trap and mid's pretty good. But if I actually apply sigma and a limit as n approaches infinity, then it's actually going to color it in with rectangles. So while I was sitting there kind of waiting, not with my arms crossed, that'd be rude, but in my mind, I'm like, I'll just sit here and wait until Dr. Staten tells me the real way to do it. Did y'all see what I was thinking? Like, okay, it's really cool and everything, but I'll just sit here and listen because he told me to, like I told you to. And I'll just wait. And at the end of the story, all we're still doing is adding up a bunch of rectangles. We're just adding up a bunch of rectangles using a limit. A limit is your Superman cape. It's your superhero power, okay? A limit let you find a derivative, and now once again we find the limit lets us find area and eventually volume. We'll start to spin these around and make really cool objects. I need everybody listening, okay? However, Leibniz and Newton about the same time in two different countries in the 1600s were both playing around with area and volume. There's no such thing as calculus back then. People studied rates of change, people studied areas and volumes, and a bunch of other stuff. Okay? Girls, derivatives are over here, rates of change, slopes. Slopes and area don't have anything to do with each other. Okay? But at some point, and I'll show you how they came up with it as best we know. And there's a book about this called Calculus Wars, like who really got to it first. And Newton gets a lot more credit than Leibniz does. In fact, I don't know if I'm saying the poor guy's name right. They said, oh my gosh, what if I didn't take the derivative? What if I just took the antiderivative? Okay? And I'll teach you how to go backwards. Some of you already know from physics, okay? But if I go backwards from this, it'll take me to this. 3x squared over 2 plus x, and if I do it from 0 to 3 and I fill those numbers in, I get 3 times 9, which is 27 over 2 plus 3. I'm filling 3 in for x, and then if I fill in 0, I get 0 for both of these. What's 27 over 2? 13.5 plus 3. You should sit there and wonder, they had to be thinking, oh my gosh, for real? Like, really? Like, that's all I have to do? Y'all, this is hundreds of years that people have been doing what I've said, and Newton and Leibniz must have just sat there and stunned silence. Like, are you kidding me? Like, will that always work? Okay? What people think the simple explanation of why that works is this. We think they were probably working on a rate like velocity. I'm going to do a really simple rate real quickly. 50 miles an hour. If I go a steady rate of 50 miles an hour, this is velocity, and I do that for 4 hours. How far will I go? 1, 2, 3, 4. What's underneath here? 200. Okay? So, what we think made them think that is if I go 500 miles per hour for 4 hours,
That's so fast.
it takes me the distance, which is the what of velocity. Distance is, it doesn't go distance, velocity, acceleration.
Yeah.
Okay, so we'll pick up there. Your homework is this. Oh! I gotta show y'all something. But you're a club, don't you?
Yeah.
Like, wow. Okay, let me show you this real quickly. Hey girls, watch. Leibniz was German. So instead of sigma, he was using a German S. In his work, he wasn't using a sigma. If you are in physics and you've seen this, which you'll see on this paper, it just means sum. It doesn't. It comes to mean integral. Does that look familiar to a lot of people?
Yeah.
Okay, it's just a German S instead of a Greek S. Only do the ones in boxes. Only do the ones in boxes and study for your quiz.
Beginning to fail. Mine starting and I
Only do the ones in boxes. things to do, I just,
Wow, you were
especially when you're just keep getting calendars. Only do the ones in boxes.
I feel bad.
She didn't change it.
I just want to be bad.
Thank you.
Did you get one or two?
Thank you very much.
Did you
Am I
get one
supposed to have
already?
one? I'm supposed to have two? Or?
No, you're supposed to have one, it just looked like two.
I don't know.